All right, let's jump right in. We're going to decode two key questions on climate dynamics straight from the 2023 Q3 paper. And trust me, nailing these answers could be the difference maker for that top grade.
Okay, so first up, we're tackling a real classic, one that honestly seems a bit backwards at first, right? Why on earth does it get colder when you climb a mountain and get closer to the sun? It feels totally counterintuitive. So let's crack this puzzle.
So here's the exact question from the paper. And pay close attention to that first word, explain. That's a huge clue. It means we can't just say, yep, it gets colder. We have to dig into the how and the why, the actual physics behind it.
Okay, so here's the absolute number one thing you have to understand. The sun's energy, it comes in as shortwave radiation. Think of it like a laser beam that pretty much zips right through the atmosphere without really heating it up. It hits the ground, and that's what gets hot. Then, the ground radiates that heat back out as long-wave radiation, kind of like the slow, warm glow from hot tarmac. And that is what actually warms the air. So the big takeaway, our atmosphere is heated from the bottom up, not the top down.
And this slide just makes that idea crystal clear. Honestly, the easiest way to think about it is that the Earth's surface is like a giant radiator for the whole planet. So, naturally, the closer you are to it, say down at sea level, the warmer you're going to feel. The higher you climb, the further you get from that radiator, and, well, the colder it gets. Simple as that.
Now for the second piece of this puzzle, air density. Think of it like a blanket. Down at sea level, gravity squishes all the air molecules together, making the air really dense. It's like a thick, cozy blanket that's amazing at trapping heat. But as you go higher, the air thins out. The molecules spread apart. It's like swapping that thick blanket for a really thin, holey one. There are just fewer molecules up there to grab and hold on to that heat, so the air stays much cooler.
So, to absolutely nail this question and get full marks, you've got to hit two key points in your explanation. First, the primary heat source is the Earth's surface, warming the air from below. And second, the lower air density at high altitudes means there are fewer molecules to retain that heat. Get those 2 points in your answer, and you've totally cracked it. All right, let's switch gears. For our second question, you need to put on your judge's robes. This is an evaluation question. You're given a big statement, and your job is to weigh all the evidence and deliver a final, reasoned verdict.
And here's the statement we're putting on trial. More frequent extreme weather events are the greatest impact of climate change. The key word there is greatest. To get the top marks here, you can't just talk about hurricanes and floods. You have to compare them against other massive impacts to really justify your conclusion. So, how do we even begin to structure an argument like that? Well, this slide sets it up perfectly. Imagine a set of scales. On one side, we've got the immediate, violent, headline-grabbing shock of extreme weather. But on the other side, we have these slower, sneakier threats. Things like sea level rise and the spread of infectious diseases. Which one really weighs more in the grand scheme of things?
Let's look at our first contender, extreme weather. There's no denying its power, right? It's visually terrifying, it causes unbelievable local destruction, but here's its biggest weakness in this argument. It's localized. A hurricane might wipe a town off the map for a few days, but it doesn't hit the entire planet all at once. It's intense, but contained in space and time.
Okay, contender number 2, rising seas. Now this is a totally different beast. It's a much slower process, driven by melting ice and the fact that warmer water just takes up more space. But, and this is a huge but, its impact is global, it's relentless, and it's pretty much permanent. We're talking about something that threatens half the world's population living near coasts. It's an existential threat to entire cities.
And our third contender is the spread of infectious disease. This one is almost silent. As the world warms up, disease-carrying critters like mosquitoes find they can live in new places. So illnesses like malaria and dengue fever start creeping out of the tropics and into places they've never been before. The real danger here is the potential for a small local outbreak to just explode into a global pandemic. So we've met our 3 contenders. You've got the fast and furious, the slow and steady, and the silent but deadly. Now it's time to put them side by side and deliver that final verdict.
This slide is where the argument really comes together. Just look at these sliders. See how extreme weather, for all its ferocity, sits over in the local/moderate zone when we talk about systemic disruption. Now look at sea level rise and infectious disease. They're pushing way over into global/severe territory. Why? Because they're widespread, they're permitted, and in many cases, there's just no going back.
And that leads us to our final verdict.
As you can see from the scales, it's not even close. While extreme weather is absolutely devastating, you can't really argue that it's the greatest impact. The sheer global reach, the permanence, and the irreversible nature of threats like sea level rise and spreading disease, well, they just weigh more. They represent fundamental, permanent shifts to our world that are incredibly difficult, if not impossible, to ever recover from.
And that leaves us with one last, really crucial thought. If we accept this verdict, that the greatest threats aren't the ones that make the nightly news, but the slow, creeping, irreversible ones, what does that mean for us? How should that fundamentally change where we focus our global efforts to tackle the climate crisis?